Yeah, thank you very much, Chris, and I want to thank the organizers of the BID program for the invitation. It brought me here after a break of some 23 years. I didn't realize how great the weather can be here. uh, so, so I had the choice of two different topics to talk about. One was scalar field theory, and the other one is gauge theory. This time I opted for gauge theory, but maybe I'll be back to talk about scalar field theory sometime. So this is a kind of talk which will start with a review and a short celebration of QCD, and then perhaps somewhat anticlimactically, I will talk about toy models for QCD, not the real thing, and try to get you interested in some of the recent work that we've been doing, which you'll hear about. So the talk, it will be largely based on these 4 papers written over the past 3 years with my colleagues at Princeton. I believe Bernardo Zahn was a postdoc here at Cambridge after he left our group, and Silvio Pufu is my colleague at the university. Ross Dempsey just finished and moved on to a Pappalardo Fellowship at MIT. And Ben Sogert is another grad student, and of course you know who this is. So let me talk briefly about QCD. So it's goes the great year of formulation of QCD was 1972-73, and the leap was made from a theory of quarks, which at the time it wasn't clear if they were really physical objects or just kind of philosophical constructs to reproduce the SU3 multiplets, flavor multiplets of mesons and baryons. And it went to the formulation of this beautiful and concise SU3 gauge theory. So of course, the quarks came around 8-9 years earlier, and then it was conjectured that they come in 3 color states. But initially, people thought of the mediator of this force as just a singlet object similar to photon. But then, actually, in this ICHAP conference, International Conference of High Energy Physics at Fermilab, which was right around 53 years ago, there was a contribution by Fritsch and Gell-Mann advocating for a color octet, namely the joint representation of gluons. And actually, I will also end with something about the joints. So this was a big breakthrough. And then this theory was formulated. This A is the joint index that runs from 1 to n squared minus 1 for SUN gauge theory. And of course, QCD is a rather special theory, which, unlike QED, is very well defined at short distances because of the asymptotic freedom. It's a part of standard model that can just stand alone and does not need to be embedded in a unified theory. And as I'll say shortly, it admits a nice non-perturbative lattice definition, which allowed for a lot of numerical work. This is the plot of alpha strong, the g squared over 4 pi for QCD. And this was already from 21 years ago when the Nobel Prize for this was awarded. And by now, the data is even better. So it's unmistakable, the matching of theory and experiment for the decrease of alpha strong towards asymptotic freedom. Well, I don't know. Actually, of course, there is the 12th talk, but which eyewitnesses say they heard it. I couldn't find the record of it. And of course, there were even earlier papers by in Soviet Union, which performed the calculation on Coulomb gauge, Hriplovich, for example. anyways, it's not some, but certainly the application of asymptotic freedom to strong interactions, I think, was first in these papers, and it kind of sealed the deal for this theory. So we now believe it's an exact theory, but it's very hard to solve. So that's the reason so many people are still working on the theory, because formally alpha strong just blows up at the scale of a few hundred MeV. And this immediately led to the confinement problem. This confinement problem really was, I think, formulated first in this paper. At least it was. But maybe Gelman was the first one who called it the confinement problem, quark confinement problem. But it's basically, it was realized that the theory does not need Higgs fields. So it's not like Weinberg-Salam theory, right? It's and we still don't understand confinement, right? It's basically that it became much more real when heavy flavors were discovered, right? Because then one could just see in the detector a propagation of a, say, B quark, and then it would hadronize and turn into jets. So in the detector, you never see a gluon or a quark, you only see hadrons. And that's very hard to explain. Basically, the elementary fields in the Lagrangian are not what you physically observe. And so 25 years ago, there were these flame millennium problems formulated, and this is actually the first one. It's still on the website, Young Mills and mass gap. And this is the formulation of the problem. It just basically says, it doesn't talk about confinement, but it talks about a mass gap, namely that you don't see gapless degrees of freedom, which are gluons propagating at the speed of light. You only see bound states of some number of gluons which are massive. And no proof of this property is known, so this is already 25 years ago, and really not that much happened towards the proof. I think mathematically speaking, probably even much simpler things are not yet known about this theory, let alone the proof of a mass gap. So the status is unsolved, and that's part of the reason why for the past 3 years and a few months, we've had the Simon's collaboration on confinement and QCD strings. Yeah, I'm happy to see one of the PIs, Matthias Gaberdil. I didn't actually expect to see him here, but we have a number of PIs, and this is an image which is made by one of the PIs, Grisha Tarnopolsky, another former student of mine, which perhaps caught on the most among all the things the collaboration has produced. You see this nice image all over. And it kind of symbolizes a proton, right? You see 3 colored objects inside this crystal ball. Okay, so how are people trying to prove confinement? Well, already a year after QCD, Wilson wrote down his famous Wilson action, actually following Wagner's work on Z2 lattice gauge theory. But this one generalized it to non-abelian gauge groups. And you basically, on each link of the lattice, you have the SUN variable, and the action is sum over plaquettes or faces where you multiply U's around the plaquette. And this formulation has been used. You have to just perform an integral over these U variables. So if you're after 3 + 1 dimensional theory, you make it 4D Euclidean theory, and you try to Monte Carlo the integral over the U's, which apparently Wilson himself didn't believe it would work very precisely, but it's one of these things that worked better than originally expected. But if you try the strong coupling expansion, where you take G, this Young-Mills coupling at lattice scale to be large, you see the famous area law of the Wilson loop. So the criterion for confinement in theories without quarks is that the large rectangular Wilson loop behaves as its logarithm is proportional to the area rather than the perimeter. The perimeter term is basically just a divergent. You can think of this as a probe quark propagating along a large contour, and the perimeter is always some renormalization of the action of this probe quark. But the area law is another way to see that there is a string tension and the linear potential between quark and antiquark. It's very easy to see in the strong coupling expansion because you see that the minimal contribution to the non-zero expectation value is where you fill in this large rectangle by plaquettes, right? You just have a filling in of this plaquette. And the number of these plaquettes will be just the area divided by lattice spacing squared. So the contribution will be 1 over g squared to a over a squared, and hence you get this area term. But of course, there is a slight problem with it, that it's not in the right regime. Instead of making g large at lattice scale, you actually need to make g very small. And that's due to the asymptotic freedom. So the so the beta function, the dimensional transmutation is basically the following: that you have the dimensionless Young-Mills coupling in 4 dimensions, which flows logarithmically, but there is a scale parameter that comes from solving this equation. It's basically lambda QCD is where the coupling nominally blows up. So you probably have seen the plot of 1 over g squared. At large mu, it just grows linearly. And then if you continue it back to where it blows up, that's lambda QCD. And lambda QCD, so in the strong coupling expansion, all the quantities in the theory are just determined by lattice spacing, which is not the physical result you want. But to achieve continuum limit, you need to make g naught small and simultaneously take a naught to 0 and g naught to 0, keeping this quantity finite. So that's what I think Sidney Coleman coined this term, dimensional transmutation. So the bound state masses and square root of string tension should be pure numbers times the same quantity. And the problem of lattice gauge theory is to estimate these pure numbers. So this is all like a heuristic estimate of where the scale at which the confinement happens, but it does not explain how it happens, right? But the fact that everything is working out was suggested already by the early calculations of Wilson and Kreutz in the mid-70s. In particular, Kreutz wrote a famous paper about SU2 lattice gauge theory. And indeed, back then, the lattices were very coarse, but now so a large component of our collaboration is lattice gauge theory, and we have some, I know very little about Euclidean lattice gauge theory, but we have experts in the collaboration, such as Mike Tepper from Oxford. And in that game, there has been dramatic progress since the mid-70s. So now it's feasible to have, for example, work on a 4 torus where each side of the torus is 1,000 lattice spacings for pure glue theory. So that is certainly tested pretty well. And people are so sure about the mass gap in this theory that they are not so concerned with it and working on more sophisticated properties. Yes?
These results verified with more recent calculations?
Yeah, they keep getting better. I think when you put in fermions, that's, of course, gets much harder, and that's where a lot of the frontier is, the implementation of theories with fermions. But indeed, some people are perfecting the theory with just the gauge fields, and there, yeah, it keeps getting better and better.
These blue masses stand as they are from
Yeah, the error bars are shrinking. Yeah, this is exactly from 20 years ago. a paper by Chen et al. Other authors are Colin Morningstar, and it's a group of authors. And it's a well-known paper on glue ball masses that keeps getting cited. They managed to, so because lambda QCD is on the order of a couple hundred MeV, the characteristic size of the glue balls is about a femtometer. And then they went down to lattice spacing around 0.1 femtometer. So it's still quite coarse, right? Because you resolve each hadron with 10 lattice sides in each direction. But definitely this can be improved, and it is being improved. So the mass gap is unmistakable, right? You see here, like the lightest blue ball is 0++, the scalar, and then this whole family of blue balls. I think by now people can shrink the thickness of these quite a bit. So in one of the things I hear from the lattice gauge theory community is, we've really established the mass gap. Why don't we get this prize? Well, I don't decide on this prize, but I think they're looking for something much more sort of rigorous. But the numerical work is a strong indication that the proof should exist. Okay, so and another thing that people have really understood very well numerically is the physical mechanism behind this area law in theories without quarks is that when you move the probe quark and anti-quark far from each other, you form this thick string or flux tube. People call it QCD string or QCD flux tube, which is also its thickness is around Fermi, on the order of Fermi. And this is highly different from QED, right? For QED, you would just get a dipole field at weak coupling. Here, you see this dipole field at distances much smaller than half a Fermi, but then it crosses over to linear potential. And one of the things where people are making progress is the more detailed dynamics of this thick string, of confining string. For example, the leading term in its action is non-Bugatti area action, but we also want to know higher dimension operators in this theory, and for that, this is a current area of research. But just this idea of interpolation between the nearly Coulombic regime at short distance to this linear regime at long distance was also already known more than 20 years ago. And this is being sharpened continuously. So now, one thing I sometimes cover in these talks is the thing that I was very preoccupied with when Chris was my student, which was the so-called warp deformed conifold model of confinement. It's a souped-up version of the ADS CFT correspondence, which actually also incorporates dimensional transmutation. And this so-called warp throat or KS warp throat is still an active area of research, but I chose not to cover it in this talk. Yes. Yeah, by correlator of two Wilson loops. I think they calculate this, right? You take on a 4 torus, you calculate wrapped Wilson loops, one this direction and the other this direction, and just calculate the expectation value that basically gives you quark anti-quark. Yeah, so to see good matching to asymptotic freedom, you have to get this 1/r here, but it's actually 1/r with an extra log r in the denominator, because g squared itself goes down as, so up to a log it's 1/r, but it's slightly different. And actually in this model it was also 1/r, but log came to the different power. Yeah, this model is still being used. this morning was gratified to see 2 papers this morning that still cited this work. And it is interesting how the dimensional transmutation happens in this paper, but I think it would take a talk on its own, right? If you are interested in an early review, actually, Chris Herzog, Peter Young, and I wrote a review around 2001, comments on the warp deformed conifold, where a lot of this is discussed. So that's one toy model. It's really 3 + 1 dimensional, and it's weakly curved, but it doesn't describe the asymptotically free gauge theory. So let me switch to other models where similar things happen. Maybe before I do that, well, this is supposed to be funny. Yeah, these are famous spherical cows. So let me switch to other. So one spherical cow model is, of course, the duality between n = 4 supersymmetric Yang-Mills and ADS 5 crosses 5. It's not a confining gauge theory, but it gives you a precise understanding of something at strong coupling. This has some people mistakenly believe that you only have to deal with this n = 4 supersymmetric Yang-Mills to have a string dual, and this is definitely not true as is seen here. You can even get confinement. But so now I will switch to 1 + 1 dimensional models, which we've been doing the last few years, and actually, yes. Mm-hmm. Yeah.
So this plot of the spectrum,
Mm-hmm.
is there a similar study of state of the art for theories of matter?
Yes, yes.
Well,
yeah, I think so. One thing that needs to be qualified is that if you take QCD with, say, 2 massless quarks, right? There is no mass gap in that theory because of a special property that pions become massless at 0 mass. So even the notion of mass gap needs to be qualified a little bit. But yes, people definitely study theories with fermions, and the problem with theories with fermions is that it's the low-lying spectrum is dominated by mesons, and it's very hard to distinguish a singlet meson from a glue ball. So fishing out what is the glue ball, where the glue ball is buried, is one of the very many papers are written on this, but it becomes not as clear cut. But definitely, yeah, there is very good agreement for more realistic meson-baryon spectrum compared to, yeah, there are arguments whether glue ball has even been seen experimentally, because it occurs at high enough mass that in real world that it's sort of in a complicated region where there are other resonances and things like that. But so in a sense, already this calculation is a bit of a spherical cow. It's a pure glue theory, but our theories like somewhat idealized problems, and claim Millennium Prizes posed for this problem, just pure SU3 theory.
It's a simplification in your model, the dimensional transmutation. Why is it toy model?
Well, that model, it's a bit like, so another model that you can study is if you add the gluino, like an adjoint fermion to SU3 gauge theory, then it becomes supersymmetric. It becomes the so-called supersymmetric n = 1 supersymmetric QCD. And our model is a bit like that, but it has actually 2 gauge groups, and they flow in a complicated pattern. So in the UV, there is still a logarithmic flow, but there is neither group reaches asymptotic freedom. So there is a UV logs that transmute into this infrared scale of bound states, but the theory is not asymptotically free. Yeah, it's a very sharply posed problem. You have to take, which I think is what the Clay Foundation is after, but forget about Clay Foundation. It's not about the money. This is what we want to establish. And yeah, it's really, you have to see this crossover from nearly Coulombic behavior and see the scale of this linear thing. So this is from work of Bali, which I think is 2002. Yeah, this continuation from the UV nearly Coulombic regime to here is turned out to be a very complicated problem. Okay, so let me now talk about some toy models for confinement, which came along in some sense long ago, but we've taken them up and actually realized some new things. So one is the Schwinger model, which is 1 + 1 dimensional QED coupled to a charged fermion. So Schwinger originally in 1962 considered the massless fermion. And what he saw is a beautiful example of mass gap generation, because there is a massless fermion, but the observable spectrum of the theory is a free boson of mass E over square root of pi. So E is the electric charge, which in 1 + 1 dimensions has dimensions of mass. So this is the exact mass of this free Schwinger boson for m = 0. And this was a kind of brief discussion of it in this paper. Then in 1975, some understanding of the massive Schwinger model where, so the massive model is not exactly solvable. But then when mass is much larger than E, it becomes weakly coupled, and it just becomes a non-relativistic calculation of bound states in a linear Coulomb potential, because Coulomb potential in one dimension is linear. And this model is also famous for being basically the first example of a chiral anomaly. You have this chiral current, and there is a quantum anomaly that electric field appears on the right-hand side. It's not conserved. And actually, I think Nick Menton was one of the first people to write a clear discussion of this. Maybe it was known somewhat earlier through work of Ken Johnson and others. And this will be important for us later on. So just for fun, I plotted here just to show you that we're not alone working on the Schwinger model. I plotted the citation per year as a function of year. And you can sort of see, like initially it seemed like a curiosity, but then there was a big jump after QCD because people viewed it as a toy model for mass gap and confinement of charges. So that's this peak, and it was solved by Coleman via bosonization of fermions. And then it sort of became a textbook material. For example, it's discussed in Peskin and Schroeder. But then it's sort of like, it's an old model, so it started dropping off. But then quite remarkably, over the past like 7, 8 years, it's just tremendous rise again. Of course, everyone wishes to write a paper like this that has many lives. And you may wonder, what is this? And in fact, the highest number of citations was 24, and this year may even surpass it. I mean, this is sort of a few months ago. But anyways, clearly something is going on. So why is there such increased popularity? Probably some of you know, but it's very much related to quantum simulators, and it's become one of the benchmark models for quantum simulators. And even some people, for example, Peter Zoller's group in Innsbruck has built an actual device with atomic chain of cold atoms. And it's also a very nice playground for matrix product states and techniques for solving it in the Hamiltonian formulation. And yes.
This model is the Coulomb branch that gives you the confinement. It's not the interaction. So.
No, it's strong interactions. You can say that it's certainly far too trivial to claim that it teaches us something about confinement in triple, because in triple, this model does not exhibit dimensional transmutation, right? It has some Coulomb potential, linear potential to begin with, but so you can say its confinement is sort of perturbative in this model. Okay, so the main reason is that I think there is a lattice Hamiltonian approach, which is a lattice gauge theory, which is a bit distinct from the Euclidean Wilson method, which has turned out to be very convenient for this model. And this was, the first paper was right around 50 years ago by Banks, Susskind, and Kogut. And it uses the staggered fermion approach, where you take a Dirac doublet and put the upper component on even sides and lower components on the odd sides. So this has become one of the benchmarks for quantum simulators. And so I'll just talk briefly about what our group did on this model. And we just started studying this model. I had no knowledge of this 4 years ago. And we thought we would try to study it to apply it to more complicated models. And there is, of course, 50 years worth of literature on this. Basically, so the essential model is that on each site there is a fermionic degree of freedom, C, which anti-commutes with C dagger, right? And then there is this fermion hopping term with the gauge, U1 gauge field sandwiched in between. These LNs are the electric fluxes that take integer values, right? So this is the Coulomb energy term, F squared, and then this is the mass term. So now in the first, and very importantly in this Hamiltonian approach, you also need the Gauss law constraint. Namely that, so here it's a very simple thing that the difference between electric fields on consecutive sides is just the charge. So in the first paper, there is actually no Gauss law spelled out, and they essentially just applied the strong coupling expansion technique to this model. A very clear discussion came much later in this paper by Hamer and collaborators. And it turns out that the Gauss law itself needs to be staggered. Namely, for even sites, you just assume the charge is C dagger C, but for odd sites, you have to subtract -1. And this is definitely the implementation that's been adopted since then. Without this -1, the space of states is totally trivial because you would not get any states. But this way, it's really at half filling, so there is a rich space of states and so on. And then there is a mass term, which everyone denoted as m times this operator. And you see that this term is changes sign under unit lattice translation. So in the staggered model, the minimal translation is usually 2 sides, because each fermion occupies sort of even, odd, even, odd. And this is basically changes sign. So you would say it breaks the discrete chiral symmetry, because there is a discrete chiral symmetry which interchanges up and down components. And in pretty much all the work, people to study massless model, they crossed off this term. But there is a problem with this, because even the Gauss law actually breaks this unit translation symmetry. So what we realized, actually, first somewhat indirectly, is that there is a way to cancel the 2 effects. and have a correct unit translation symmetry, which is, yeah, just one comment that there is a Jordan-Wigner transformation, which is convenient to adopt, where you introduce spin variables, and then you can solve the Gauss law constraints on an open line and have this very explicit sort of XX model for the kinetic term. Then there is a mass term, and then there is a Coulomb term. Okay, and yes. Yes, yes. Yeah, but it's exactly, I think what we figured out is a better implementation of this discrete subgroup of chiral symmetry that has to do with this unit lattice translation, which no, it's actually in the one flavor model it's broken, but then I'll show it in the next slide. So here is what we realized. So because of this -1, you see that on even sides, the possible charges are 0 and +1, and on odd sides are 0 and -1. And this is, so we have an expert here, Frank, who's worked on this model a lot. And I think this is the implementation also even in the experimental devices, they implemented like this. You can also adopt periodic boundary conditions where this unit translation symmetry is manifest, or you have to work on an infinite chain. So here is the punchline, that the somewhat surprising result that instead of taking lattice mass to be equal to the continuum mass, you have to adopt this shift, this exact shift, which while it goes to 0 in the continuum limit A to 0, it actually affects a lot the strong coupling expansion and the rate of convergence. And the reason is that the point m equal to 0 or m lat equal to minus e squared a over 8 is actually protected by a discrete anomalous chiral symmetry. Namely, if one makes a unit lattice translation, which is like a chiral rotation by pi over 2, that is equivalent to shifting theta by pi. So theta term gets shifted by pi for this one flavor model. And then one can indeed see that at this point, the offending terms exactly cancel. So this is the right point, basically, to be, this is the right relation. And there are other ways to understand it. For example, if you don't adopt this shift, then the convergence to the continuum limit is violated by terms linear in A, which is actually very, very large terms. You want usually the violations to be at least of order A squared. So this term is a kind of anomaly, if you will. So let me just show you a couple things to convince you. Yes. Right, but on the lattice there is still dependence on theta. Yeah, yeah, right. Yeah, I mean the lattice doesn't have exact continuous chiral symmetry. Yeah. Yeah, in the lattice, the theta enters here. So for example, the model with theta equals 0 is where these terms are integer, and theta equal pi is half-odd integer squared.
Do you know something similar happens for, so if you do CP1 sigma theta equals pi, you know it's gapless, but and there's a nice spin chain realization by the XXC spin chain. Heisenberg. Spin chain. I mean, it feels that this cancellation must happen there in order to make that massless.
Yeah, that would be interesting to think about. That does not have chiral symmetry, though, right?
No, but it has the same. same translation symmetry is all.
Yeah. This whole issue of unit translation symmetry, it crops up in many models, including bosonic models.
Yeah.
Some, I think some related work has been done. I know, for example, Tin Suleiman Pasic, he wrote papers on these bosonic models at theta equal pi also. But for the advantage of the fermionic model is that it's actually completely UV finite. There is no divergence at all. So some interesting quantum critical phenomena actually are embedded into this model. And so in fact, that's what I was going to talk about. So there is a famous, at theta equal pi. So theta equal pi and positive mass is same as theta equals 0 and negative mass. It's just so there are two ways to think about this quantum critical behavior, but perhaps the more physical is theta equal pi at positive mass. And this also has a long history. There is an easing phase transition that for small mass, there is a unique vacuum, and for large mass, there is doubly degenerate vacuum. It's very easy to see in the bosonized formulation. Just classically, you see a transition between a symmetry breaking transition. And it really does describe 1+1 dimensional easing model. But the critical value of mass always seemed tantalizingly close to 1/3. In fact, there are many papers. But equipped with this mass shift, actually, you gain a couple orders of magnitude in precision. And in this paper, they showed decisively that it's not exactly 1/3. So that's a bit disappointing, but better, because I think some people wanted to prove that it's exactly 1/3. But then another thing is the strong coupling expansion. This actually goes back to the original Banks et al. Paper, because they started doing the strong coupling expansion, and mu is this lattice mass parameter over E squared A. They always took mu equal to 0 and extrapolated this series, and the results really were not great. I mean, they were at best like 15% for some quantities. But so after the mass shift, actually, to describe massless model, instead of mu equals 0, we have to take mu equal 1 minus a quarter. And then it actually, but the extrapolation is extremely smooth, and the result you get is, it's almost too good to be true. It's less than 0.1% of the exact value for this series. I mean, to do precision calculations, you don't do this. You actually do the numerical work, which was, for example, done in this paper. But without the mass shift, you really lose a couple orders of magnitude in precision from what I understand. So this is one amusing thing. But now let me try to tell you something a bit maybe more interesting and more related to QCD. Yes.
But from the point of view of numerics, you don't have to do anything different than before. It's just about how to interpret the results.
Well, you just work at a different point in parameter. Yeah. Yes.
That's the only thing that changes.
Right. Yeah. It's same model, just different identification of parameters. Yeah, it's important for low mass region. Like if you want to work at very massive one, it's probably not that important. But to get this chirally symmetric point. Okay, so now let's. Any more questions? So now let me talk about the two-flavor Schwinger model, which is another classic model from the old days. And that one was pioneered by Coleman in a very nice paper called More About the Massive Schwinger Model. So now if you make both flavors massless in the continuum limit, this is described by a CFT, which has SU2 cross SU2 symmetry. SU2 level 1 WZW model. And it's just a self-dual scalar field, basically. So now there is no mass gap in this model, but we will study what happens in the low mass region. So one interesting thing is that this model has a charge conjugation symmetry, and it's preserved by either theta equals 0 or theta equal pi. And at theta equal pi, it can be broken spontaneously, which is reminiscent of what happens to CP symmetry of QCD. In fact, there is a very strong similarity between this model and phase diagram at theta equal pi and QCD with two light flavors at theta equal to pi. So this is from our paper a couple years ago. This is the phase diagram at theta equal pi. And you see that there is a region with two vecua, which is bounded by these two easing lines. I told you about this easing line. This is this M critical, which is about G over 3. So this boundary approaches G over 3. And this is this region with two vecua. And actually, a particularly interesting region is what happens for M1 equal M2 along this diagonal line at low mass, which I will talk about. But one interesting thing is this is actually from Kreutz's work, which I heard in his conference talk a couple years ago. And he conjectured this phase diagram for QCD. It's really qualitatively the same. He just was using theta equals 0 parameterization. Theta equals 0 with one quark mass negative is same as theta equal pi with. Yeah, this is SU2 level 1. This is C equal 1, just a compact scalar, self-dual scalar. And this is the region of broken Z2 symmetry. Just flavor two fermion masses. Yeah, there are two fermion masses. You can dial them independently. Yeah. And in QC. Yeah, from the mass. Yeah, I'll show this in 1 second. Yeah, this. But this, if you ask, say, what happens in QCD with two light quarks, M up and M down, there is also supposed to be this region of broken Z2 symmetry. If you go to theta equal pi convention, you will just rotate it and it will look the same as this. And these papers were written by Kreutz over the years. I actually was not aware of them initially. And the transition, when you cross from the unbroken to broken, it's called a Dashian transition. It's also was studied more recently by Gayota, Kapustin, Kamargotsky, and Seiberg in, I think, when was it, 2017, something like that. Okay, so let me go back to this paper by Coleman where he set up the study of this model. So there are two Dirac fermions, and you can bosonize them just a billion bosonization and introduce two bosonic fields, phi1 and phi2. And then you form two combinations, basically the plus combination and the minus combination. The plus combination gaps out when you integrate out the F mu nu field, and it becomes this massive Schwinger boson. But then there is a light field phi minus, and the question is what happens to its dynamics at scales much smaller than G. So indeed, if you just give say for theta equals 0, just generic mass, and you compute the leading relevant perturbation, it's a sine-Gordon model. You have cosine of root 2 pi, phi minus, and this is a relevant operator of dimension 1/4, 1/4. So it causes RG flow and creates a mass gap in this model. And Coleman already, he used some, one can just do an RG estimate of how the mass gap scales with M, and it's M to the 2/3, right? But, and this in itself is, people are still trying to check numerically, but it's, but notice that for theta equal pi, this term vanishes altogether. And it really, actually, Coleman left it as a puzzle, precisely what happens at theta equal pi, which is clearly a very singular point here. So people were even speculating that some, maybe for theta equal pi, there is a critical line. So, but what we believe is that the gap actually becomes exponentially small, essentially due to dimensional transmutation mechanism, similar to what happens in QCD. So this, if you go to the next order at theta equal pi, you basically integrate out this 5+ field, and you get a sine-Gordon model. But now this cosine has √8 pi, so it's really a marginal operator. So now this becomes like a sine-Gordon at the marginal point, which undergoes the Berezinski-Kosterlitz-Saulis flow. And somehow this, in 1976, maybe it was already known, but maybe did not percolate fully how this whole thing comes together. So in fact, so this is the phase diagram that has already won a Nobel Prize, so must be correct. But usually people talk about flow to the fixed line, right? Flow to the CFT. While we are actually in a different region where you flow along the SU2 symmetric line away from the CFT. And if you use these famous beta function equations, the BKT equations, you find that this dimensionless coupling, m²/g² undergoes RG flow with essentially the same beta function as in QCD, right? It's minus m³ So then, again, estimating at what scale this coupling diverges gives you the energy gap, which is e to the minus a constant times g²/m². So at m much smaller than g, this is really a tiny quantity, right? So unlike the power law gap that appears away from theta equal to pi, here it's truly minuscule. So I think this is a pretty QCD-like behavior, which maybe is worth taking another look. In terms of numerical work, it's much harder to establish, right? Because to see exponentially small quantities is hard. But we did try it with this lattice Hamiltonian with this improved mass shift. And now, very important observation that in this case, there is actually a discrete chiral symmetry without any need to shift theta in this case. It's truly a special symmetry of this Hamiltonian at the mass shifted point, which is the lattice translation by one side. So here the anomaly cancels, so basically this discrete anomaly cancels. And so this is a plot from the original paper where we tried to use the estimate of correlation length from entanglement entropy. And it looks qualitatively like our conjectured phase diagram. This region where between these two lines is very, very narrow. It's really exponentially small. But now we have some new work going on, which I think is further convinces us that this estimate and effective field theory for energy gap is correct. Oh, this is basically the MRG, yeah, just the MRG. And yeah, just a comment about theta equals 0. So this group of Etsuka Ito and collaborators. Also, using the mass shift, they seem to have gotten pretty close to the right value of for just the mass gap and ratios of masses. Because one interesting QCD-like fact about this theory is that there is an SU2 triplet of pions followed by a singlet sigma meson, just like in two-flavor QCD. But the sigma meson is a bound state in this case. It's not a resonance. And Coleman predicted that the ratio of its mass to the mass of the pion is exactly √3 based on this integrable sigma model. And this is only in the limit when M is much smaller than G, which is hard to reach in practice. But they obtained pretty good results, like within a few percent of the square root of 3. So even this regime is still like being understood numerically. So I think this QCD-like regime of theta equal pi to flavor QCD is pretty interesting, and we're still looking at it some more. Definitely, it's interesting that in the lattice model, there is now an exact discrete chiral symmetry without the need to shift theta by pi. So it's really a symmetry acting on states of this model. Okay, so I'm about an hour into the talk. I can talk about another topic briefly, or maybe it's a good time to pause to see if there are questions, because I wanted to switch to another model.
Simulations for some transition half a century, pretty good. So,
Mm-hmm.
is there any reason why these things that people are using, like quantum Monte Carlo, for example,
Yeah, I think probably most of these simulations concern the flow in this part of the phase diagram, right, where you go towards the critical line.
Yeah. If anything, it's easier once you cross it. You have mass cap no matter how small.
I see. Oh, this. Mm-hmm. You mean like on this side of the separatrix when you go to?
I mean, maybe not.
I confess that I'm not an expert on it. I mean, we did try to look up, but what is known. I mean, a lot of when you, I don't know, ask ChatGPT or something like that, it will primarily talk about this logarithmic approach, right, to the. Well, in what we're doing, there is no sign problem. I think it's just. Yeah.
That's not a physicist in Princeton.
Yeah, no. Yeah, I think for this specific model, so we have this model, we're concerned with embedding it in a very specific lattice gauge theory, right? That's why I think it's interesting that the model comes with a specific regulator, right? So we start with this spin model coming from this lattice gauge theory. And only in the regime of small mass do you have a separation of scales when M is much smaller than G. Otherwise, it's just like not. So you have to reach the regime where this effective field theory is good, right? But I'm indeed, like, this is one of the best explored models, and yeah. So I'm sure you're right that this emergence of this mass gap has been, yeah, we should, if you actually have references, I would like to. Mm-hmm. Mm-hmm. Yeah, I should. Yeah. No, we found some papers, but maybe didn't study them. Yeah, for the definitely finding the mass gap, which is so tiny, naively is hard. But
No, it is.
yeah, but you can do. Yeah, there's pretty strong evidence that this is really what happens in this two-flavor Schwinger model.
Phase diagram with the two masses.
Mhm.
Yeah.
Yeah.
Yes. What do you see the energy gap here?
Well, you have to go down to this very near the origin along the diagonal. Yeah, this plots some. Yeah, this just has some correlation length. I think different colors. This is not the
That's
energy.
because of the correlation.
Yeah. Mhm. Yeah, but you want to be like in this region here, which it has a very large correlation length. Okay, so now let me just talk. I don't want to talk indefinitely, but there is a somewhat different model that I've spent a lot of energy on, which is a non-abelian model, which in some ways is a bit like the one-flavor Schwinger model, but in a non-abelian setting. It's probably most of you have heard about the 't Hooft model, right, which is just a carbon copy of QCD, but to 1+1 dimensions, and it has large n limit and say 1 quark or 2 quark flavors. So 't Hooft solved it in the light cone gauge using and derived this beautiful equation, which more recently is sort of subjected to renewed look using integrability techniques. Actually, one of our students just submitted a paper a day ago on an improved solution of the 't Hooft equation. And but another model that one thing about this 't Hooft model is that it doesn't have any dynamical degrees of freedom in the adjoint representation. Because in 1+1 dimensions, gluons are not dynamical. So what one can try to do is to add them by hand. For example, add an adjoint scalar field, or even better, an adjoint Majorana fermion, which is a bit like a gluino, right? And this model has turned out to have very unusual and counterintuitive properties, including actual disappearance of confinement when this gluino mass is sent to 0. And it also is a nice setting for non-invertible symmetries. Actually, I know that Zohar Kamargotsky gave some review talks here, and he and collaborators wrote a nice paper on non-invertible symmetry application to this model. Okay, so here is the model. It's very simple to formulate. It's just the usual, and this psi is a Majorana adjoint, and then you can add the mass for this fermion. I started looking at this model already like 33 years ago, and it's not solvable like the 't Hooft model because there is an infinite system of coupled equations even in the light cone gauge. Because you can take these gluinos and turn them into a closed string. So there are different closed string states with different number of bits mixing together. But still one can numerically calculate fairly well what are the masses of lowest lying bound states. And for m equals 0, there is definitely a mass gap. And the lightest bound state is a fermion, like roughly a 3 gluino state, and the next one is a 2 gluino state. It seems it's a little surprising that the 3 gluino state is lighter than the 2 gluino state, but okay. And this model also, even much earlier, Witten pointed out that this model has a kind of discrete analog of theta vecchia, because one can, for example, put a fundamental charge at minus infinity, a quark at minus infinity, and anti-quark at plus infinity. And that's a new state of this model. It's a new sector of this model where you are kind of living inside the QCD string, or you can put two quarks in one end and two quarks on the other end, and so on. So there are actually n different sectors which measure these the number of probe quarks at spatial infinity. And all these features come in when you study this model in some detail. So another thing is that in you can prove that there is a mass gap by studying the far infrared dynamics, where it becomes a gauged WZW model or a coset model, where you first take Majoranas and replace them by SON squared minus 1 level 1, but then you have to gauge the SUN level and currents. And the difference between central charges is exactly 0. So this model has infrared central charge, which proves that there are no massless bound states. There are only massive bound states. And since this coset model is topological, it does not have a notion of area, basically. Therefore, a large Wilson loop in the fundamental representation cannot exhibit the area law. This is sort of this slick argument that something interesting happens for this massless model. And so this is actually an argument I heard from Witten, but we initially conjectured it based on other things, that there is a perimeter law for m equals 0. In other words, the string tension disappears. But physically, it's a very mysterious thing that a joint gluinos can screen fundamental probe quarks, and it's still not completely clear how this happens. Questions? Okay, so what did we do more recently? I mean, work on this model largely stopped for many years because of ADS-CFT, and but then in 2019, there was an interesting paper by Charman, Jacobson, Tanizaki, and Unsal, which basically criticized what we were saying before and said that it might not really be correct. And this is due to 4-fermion operator, which appears in this model, which is of Gross-Neveu type. It's a kind of double trace operator that they worried can get induced. But this term actually violates the UV finiteness of the model because it has logarithms in the UV. And this paper by Komargotsky et al. Showed that it breaks non-invertible symmetry. So unless you add it by hand, it will not be induced. But this still leaves a question. Suppose you put this model on a lattice. Will there be this term there? Will it be confining or not? And this prompted us to try to write down a lattice Hamiltonian for this model, analogously to the Kogat-Susskind Hamiltonian for Schwinger model. So to do it, you have to take n squared minus 1 Majorana chains. I wanted to do it for a long time, but I was never sure precisely how it's going to work and whether there is a sign problem or a doubling problem. But it turned out to be very doable. You take n squared minus 1 Majorana chains and couple them together with link gauge fields. So this was in a paper about 2 years ago. And this model really appears to work well, even on pretty small lattices. Yeah. It has some, but as far as I can tell, it does not have non-invertible symmetries.
So this non-invertible symmetry of the continuous.
Yeah. But it has I'll just, one interesting symmetry that it has, which I think is invertible, also has to do with shift by one lattice spacing. because it turns out that you make a shift by one lattice spacing, and it shifts you from the sector with no with trivial sector to n/2 sector, p equal n/2. And we see it very explicitly in the SU2 model. We see exact degeneracy between the n/2 string sector and the 0 string sector. That's built into the model. But I think that's not enough to see the full structure. In particular, it's not built into the model that the string tension automatically vanishes. You have to really do the numerics. But one thing that this model allows you to do is, for example, study the gluino condensate, which it was not done before, and we did it for different sectors and for SU2 and SU3. And it agrees actually with the work that people later did on Euclidean lattice with Wilson fermions. And here is maybe the most interesting things to come out of this model, which is a paper that my colleagues put out just a month ago. They advised the new matrix product, infinite matrix product state method, which I cannot explain to you, but I think Silvio Pufo will be giving a joint London triangle seminar in October, where he will probably talk about some of this. And here is a plot of string tension as a function of mass. And sure enough, it really hits 0 at 0 mass. So this topological argument from the gauge WZW model is really correct. I think these 4 fermion terms really are not induced, even in all these lattice models people tried so far. So I think if you want to play with Schwinger model and find that there have already been too many papers on it, I think this could be a good alternative. It's almost no one but our group has studied this Hamiltonian numerically, and who knows, maybe we missed something. So it's.
You think the same also for other representations now, because
Yeah, exactly, yeah, exactly. Yes, yeah, that was the main result of Komorgotsky et al. So they, well, it's hard to tell whether it's present or not on the lattice, but I remember there were a lot of discussions at the time when people were arguing about this, and what they wrote, Sharman et al. Wrote, is that this is allowed by all the regular symmetries, and usually whatever is allowed will be there on the lattice. Somehow that's not how it happens in this. Yeah, it's really not there, and this is a very precise result, I think. The reason I didn't even need non-invertible symmetries because this term creates UV logs, while without it, the theory is just finite, the continuum theory. So you could just, as a field theorist, have an argument why it's not generated. But still, it's not a proof. I mean, it's like a very convincing numerical. But this is very interesting. It just shows that confinement can actually disappear even in a model where you would ask just about anyone, and they would tell you this model is confining because it has a perturbative linear potential, but somehow this potential gets screened out by in a mechanism which is a bit hard to understand. And then let me just end with another surprise about this model, which was also noticed years ago, but we understood it better very recently, which is that when you make this gluino mass to be this specific value, the model becomes supersymmetric. And there was some numerical evidence for this also, but it's also kind of counterintuitive, because why would you have this gluino massive? We're used to massless gluino giving symmetry. And also, there is no superpartner in the Lagrangian, right? There is no glue on the But so we wrote a paper on this with great help from Witten, who realized basically what the supercurrent looks like. And its conservation is very interesting. It really relies on an operator anomaly in the algebra. So this is the concise covariant supercurrent expression. And basically, the anomaly equations include this F term. So it's a kind of non-abelian version of Schwinger's term. And if you write in components the supercurrents, you see that the conservation equation arises from cancellation between just classical equations of motion, where the mass term affects them, and quantum anomaly terms. And it really requires this massive glue to do that. And we also found some models with additional matter which are actually gapless and have full supersymmetry. For example, you can have a model with three adjoint Majoranas, one massive and two massless. And that model has full supersymmetry and gapless sector. And another consequence is that this supersymmetry can be spontaneously broken in the sector with the QCD string. And this is also, this lattice model shows this result, that right at SUSY mass in the string sector, there is the mass gap basically goes to 0 there. Okay, well, yeah, sorry for rushing a bit through this last part, but let me just summarize it. So the number one message is that we're certainly nowhere near a rigorous proof of confinement in a symptotically free 4D gauge theory, but even on the mechanism of confinement, there is no broad agreement what's really it. So that's why it makes sense to work on other, perhaps simpler models. And so, for example, this two-flavor Schwinger model at theta equal pi seems to build dimensional transmutation into a finite theory of just lattice fermions. So maybe here it will be possible to understand more precisely. And then there is this adjoint QCD2 model, which is a bit like a non-abelian version of Schwinger model. And various lattice Hamiltonian approaches certainly seem like a great tool in 1+1 dimensions, because the Gauss law largely eliminates the linked degrees of freedom. And who knows, maybe some of this will become a part of experimental physics one day. So, okay, thank you for your attention. You mean supersymmetric QCD?
No,
the 2D.
Did people study the scattering of kings between the vapor there? Because there are many vapors actually, the symmetry breaking, and you have kings between.
Yeah, the main walls. Yeah.
You don't people study the scattering?
No, I don't think so.
Some predictions from the S matrix for some properties, but I didn't know.
Yeah, these domain walls is actually a very interesting question also for these lattice models, like how to. Yeah, no, I don't think this has been studied at all. Just a regular Gross-Neveu model. In 1+1 dimension for large n, or well, I mean, that one is analytically solvable. That's not a gauge theory. So one way to implement it could be with as a Yukawa model. Yeah, that we have not looked at. I mean, of course, there is a lot of literature on that. But in that model, there is no. Yeah, you generate a mass gap, right? But there's no notion of gauge fields or confinement. Right.
In the lattice gauge theory for the four-dimension that discovered the blue books, is it possible to massage this problem to see what to guide the theory? I mean, like reduce dimensions or change the group, or to see really what gives rise to this?
Well, one direction which many people are pushing is large N limit. This is what Michael Tepper and his group have been doing a lot. Like basically seeing if there are, they can do it for finite N up to, Croyd started with SU2, now people can do explicitly like SU14. And you actually see that the 1/n corrections are often very small. So trying to see if there are any simplifications in this 12th large N limit. Yeah, there were dreams that the theory could become integrable in that limit, but there is no evidence of that at the moment. And then another interesting model on which there is work, but not as much, is indeed adding a gluino. Like then you have supersymmetry or it's softly broken. So that model should be easier to. But on the lattice, it's harder because you need to implement the single gluino correctly. I would call it's kind of accidental, yeah, but you can say it like this. The reason you suspected there could be supersymmetry is just a free adjoint field, right? Has a supersymmetry, a massless adjoint has a supersymmetry with supercurrent trace psi cube. And then adding the gauge sector somehow lifts the mass from 0 to square root of g squared n over 2 pi. But from the point of view of the gauge theory, it does look a bit, it's certainly non-linearly realized, right? Because the super partner of psi is basically psi psi. So it's not it's not in the Lagrangian, it's a composite operator.
Let's thank Igor again.